This is a demonstration of a vibration absorber set up in the Dynamics and Solid Mechanics lab in Building 11 at UTS. Here we have a beam which you can see behind the plexiglass here, which is there for safety, mounted to a rigid frame. The beam is pin jointed at each end. We have 2 pins at each end, so it can bend as a pin jointed beam. There's a motor behind here with a coupling with a shaft, a couple of universal joints in the shaft, connected to a pair of counter-rotating masses. These counter-rotating masses are misbalanced, and they rotate at the same frequency but in opposite directions. And the result of that is that any horizontal forces that occur as a result of the misbalances are equal and opposite to one another, so they're cancelled out. However, any vertical forces are doubled essentially from one of the counter-rotating masses, so they are in phase with one another and they fluctuate up and down. So we have a sinusoidal or a harmonic forcing function operating on this beam. Attached to the beam is a mass. It's actually a pair of masses. The second of these 2 masses can be either fixed with the main mass of the beam. The beam acts like a spring essentially to this, either a single degree of freedom system here, or if we undo this wing nut, then this mass, this second mass, can move independently to the other mass. So it's not quite a perfect tuned absorber or vibration absorber system. In a typical vibration absorber system, we would have a mass to begin with, and we would attach a new mass and spring to that to make a 2 degree of freedom system. In this case, we're actually effectively taking a little bit of mass off the original mass, and that becomes M2. And we have 2 springs here. These are essentially just our K2, and then we have a mass 1 up here, and then we have a K1 that comes about as a result of the beam here. We can use this motor speed controller over this side to drive the motor at various different speeds, and we can fluctuate those speeds such that the harmonic forcing function coincides with either of the single natural frequencies. When we have a single degree of freedom system, we have 1 natural frequency, or the 2 natural frequencies for the 2 degree of freedom system. And so we can essentially tune those various different mode shapes, and we can see the motion very nicely. With a typical tuned absorber system, we have 1 natural frequency, and when we add another mass, the idea is to split that natural frequency into 2 new natural frequencies, such that if we have an operating speed of a piece of equipment on that structure that coincides with the original natural frequency, we have a dead band in between these 2 new natural frequencies, and we don't have the rotating misbalance resonating the system. That's the point of a tuned absorber. So if I turn the motor on over here, it gets a little bit noisy, but that's because we've got misbalances in here. And if I find the first natural frequency of the beam, which is at approximately 18.5, I think, hertz, around there, 19 hertz maybe, you can start to hear there's much more vibration. This is our single degree of freedom system natural frequency, actually occurring at around about 19.5 hertz. If I turn the motor speed down and then I release the second mass, we now have a 2 degree of freedom system, and its natural frequencies are different from the previous natural frequency for the single degree of freedom system. One of them is lower than the 19.5 hertz, the other one will be higher. So I'll just retune the speed controller, and so around about 15.7 hertz. Here you can see the first natural frequency, and both of these masses are moving together. That's the first mode. It's difficult to see it under normal lighting conditions, but we will do some close-ups where we can see both masses moving, and we'll use a stroboscope to accentuate that motion. If I increase the motor speed control to a higher frequency. I think you can hopefully hear the motor speeding up. I then get my second resonant frequency for the 2 degree of freedom system, which is quite loud. There's lots of motion. It's approximately 26.7 Hertz, and in this case, the two masses are moving away and towards each other, like this. It's also worth noting that this entire system is sitting on an anti-vibration setup here to eliminate any vibrations from this heavy rigid bed being transmitted into the floor of the laboratory when we run this experiment.